So we're going to get to a little more technical discussion of what's going on under the hood. And we're doing this not so that you can go off and implement your own I/O transformations, but so that you can have a little bit better understanding of what's going on at things like HDF5, parallel CDF, or other layers. No matter what context you're in, these sorts of transformations, even if they aren't in like an MPI I/O context, are still going to have valuable, still valuable tools to have in your toolbox as we get to larger scales and have to manage more and more complicated data sets. Now, even though it's 2014 and distributed systems are not a new thing, the idea that there are multiple clients writing to the exact same file is still a bit of a challenge for a lot of these file systems. There's a variety of reasons, but if you imagine, as you said, files are spread out linearly in disk, and they're often segmented into these blocks, and so the application, the operating system, this is will manage that concurrency by sort of partitioning the file into these locking units, and then we'll issue in some form locks for each one of these different regions. And if you are spanning two different lock regions or more, then you have to have a little bit more overhead than if you somehow manage to fit all into one lock region, obviously. But anyway, this is an additional complexity when we think about how we're accessing data, especially for writes. It's a little bit less of a concern for reads for most people, for most file systems. So why would you go through this overhead? Well, you can allow for some distributed caching to happen. You ensure that some relatively strict consistency semantics are applied. Those strict consistency semantics may not be relevant to some applications, but since they're relevant to some, they're implemented at this low level. So you can think a little bit about how your data, again, the impedance mismatch between the way the application lays out data in some 2D array or maybe with a header, and how that application level thinking maybe not map directly perfectly to the low level storage format. So take your 2D array, everything's nice and regular, first variable, second variable, third variable. There are 2D arrays, but okay, sorry, not different variables, but they are rows of a 2D array, sorry, in a row major language. There's no header, everything happens to fit in nicely, but if we push things off just a little bit with a small header, which you can imagine would happen for all kinds of file formats, now all of a sudden these variables, which initially fit in very nicely to two lock units per row of the array, now start straddling lock units, and this creates a synchronization point, a bottleneck when you do the I/O. It gets even more complicated if instead of rows for a row major language, you're doing a block distribution, and now you've got more coordination that has to happen, not just your own lock unit, but your neighbor's lock unit gets involved, and there's a lot going on here. Again, we'll talk a little bit about how the lower level library can help mitigate that, but this is an example of what would be a good example of a good nomenclature for this might be an OS level or a system level, a kernel level lock. This is not the kind of locking that the user requests to coordinate and synchronize access. This is happening in the implementation of the file system, and as a result can sometimes be difficult to mitigate at a user level. So one transformation is to align to block boundaries and do some massaging that makes things more efficient from a locking standpoint. Another transformation is to take what is an interleaved file access here, where you're pulling different elements out of an array, or you've got a particle simulation, and so you want the particles that have kind of gotten scattered through the file. You're transforming data from sort of a spread out layout, a distributed layout in file, into contiguous chunks in memory that you can then operate or do Fourier transforms on or whatever. You may want to keep this structure in the file because it's helpful for your collaborator to understand something. It's helpful for one of the data models or data structures you're using for queries or whatever. There are a bunch of reasons why you may not just dump out contiguous chunks to the file. And so these transformations happen in the library and help reorder the data in a way that is both good for you and good for the file system. Again, calling back to the graph that Rob showed earlier, the other transformation you can do is to reduce the number of operations. It's in all kinds of storage contexts. The small operations are latency dominated, and the bigger operations are bandwidth dominated. So if you can issue fewer larger requests, you then pay the latency cost once, and then you're hopefully the lower cost of the bandwidth penalty is paid. And so we see this all the time in computer science, right? The caches you don't do byte caches, you do pages and page tables and things like that. Same idea here. And like your store RAID device, you can think about something called a data sieving optimization, where let's say you needed a subset of data, a non-contiguous piece of the data for whatever reason. Your scientific structure dictates that you only want every other block or some number of blocks out of this data. Well, for a write, you can do this data sieving step. Read the whole region of the memory from, this may be like, say, a few megabytes. Read into memory into a temporary buffer, and then you'll throw away, you'll sieve out the data you don't need, so you can update the memory that you want. You are moving a lot of data, but you only did it once, so there's a trade-off here. Obviously, if you only needed 2 bytes out of a 10 megabyte chunk, you'll be wasting too much data. If you need 99% of that data, then it's a good payoff. And of course, there's a spot in the middle where it's harder to say. And that's very dependent on the file system and the density of the request and all kinds of other details. But this is one of those tuning parameters that you might not worry about right away, but we might do as a second or third step towards tuning. The other big optimization that happens in the MPI library or any middleware library is this idea of reorganizing data, both to reduce the number of clients and to increase the typical request size and mitigate any locking overhead. So you have this example where everyone's got some piece of memory they want to write out, but they have a non-contiguous layout in file. So we can take advantage of the fact that you might have a very fast server network, and you might have another separate fast communication network. We'll use both of those, right? We'll reorder the data over the network and then write it out in the fashion that is both good for the file system and gives us the layout that we need. So we call this two-phase collective I/O. Phase 1, reorder the data. Phase 2, write the data. There's a 0th phase where you sort of compute the schedule. For some systems, that's expensive. It's kind of interesting, but not really super pertinent discussion right now. But there's a lot going on, hidden away under the library. In fact, I'd like to say there's so much going on that quite a few years back now, I guess, a colleague of ours could get a supercomputing paper describing some different ways of doing this and the benefits they have to different file systems. In the most common of these libraries, Romeo, there's this idea of file domains. And the most natural way to do that is look at the first request and the last request and just divide it up among aggregators. But if you don't pay attention to the underlying file system, you get these regions where the aggregators here, it may be hard to see in the back, but these aggregators are sitting on top of a lock boundary. And again, as we talked about a few slides back, that can cause a bit of a headache. You'll have to service the left side and then the right side, and that serializes things and hurts performance. We just make a small adjustment and align these to lock boundaries. That can help a lot for GPFS. However, it has no benefit. In fact, it hurts luster. In luster, you want to do some reordering so that you are talking to different servers, not worrying about lock boundaries at all, but organizing things so that each aggregator, in this case, the A1 here, is sending its orange slice of data to one OST. Now, again, you wouldn't do this on your own. If you did it on your own, you'd probably get it wrong. Not because you're not clever, you're all very clever. It's just that it's sophisticated enough that the details are hard to get right the first time. Now we can look a little closely about how these things pay off with a couple different examples here. There's an application called S3D. It's a turbulent combustion code. It's using 3 and 4D arrays to checkpoint some different variables about as it models the combustion of a jet. A jet combustion. This is a fuel combusting in a combustion chamber of some kind. You may imagine an engine or a rocket or a plane or anything like that. But of course, again, as we said in the beginning, you're not going to model this on a desktop, on a bench top. You can model and visualize it, and then you can see if this is turbulent or not, or if it's efficient. But as with all of these large domains, they're checkpointing periodically to save their work. What's the best way to checkpoint? Well, this is going to be a kind of a long in the tooth story, but it's really a compelling one, even though it's a couple machines old now. If you were to turn off all the optimizations that are going on in MPI-IO, all the transformations that we talked about, and had every process write each cell of these 4D and 3D arrays, it'll take you half an hour, in this small example, maybe more accurately, it'll take you 100,000 operations because each cell gets written out. The optimizations to do data sieving, to do two-phase have all been turned off, and there's no care for alignment. There's 6 megabytes written out, and it takes half an hour. Now, you could probably write half a megabyte on text in half an hour, but this was going on pretty poorly here. So we turn on data sieving. Now, again, data sieving is moving a lot more data. In this case, almost 8 times more data. More than that, a lot more data. But the runtime is cut by a factor of 100. Again, moving more data is fine because the latency of each block is paid once. There's some discarded data, but you're still coming out ahead. You do a lot fewer writes, only 81 instead of 100,000. There's fewer unaligned accesses because you have fewer requests. Again, every request you make is unaligned. So let's go one step further. The two-phase buffering, 5 operations, 1 for the header, 4 for the variables. Everything's aligned nicely. Only a few operations are unaligned, and that's just because this was writing to parallel net CDF, and the variables weren't quite tuned exactly right. But our runtime is down to half a second, even though there's a lot going on. We're exchanging data over the network, and we're reorganizing the data. We move 6 megabytes, half a second. That's getting closer to what you'd expect from a leadership class storage system. Now, the numbers, if you were to do this experiment today in 2014, would look a little different. The sizes of data, the numbers of operations, but the overall lesson that these operations pay off in the long run is still good. And you can use a tool, which we'll talk about after the break, called Darshan, to collect these kind of low-level statistics and see for yourself how your application is behaving or misbehaving. So we're going to go, so again, there's this layer, this relatively new layer, the I/O forwarding layer, and while vendors haven't really implemented a very sophisticated I/O forwarding layer, in research, we've got a lot of good ideas on how we could do something clever between communication and storage in a little bit different context than like the MPI-IO library will let you do. In this blue section, it's a big blue blob, but for Mira, this big blue blob is represented by about 1 million MPI processes, 760,000. But and if you had each one of those order 1 million processes right to the storage system, you'd be dealing with about 1 million system calls and about 1 million clients. And so most of these file systems would see that as a pretty aggressive denial of service attack. Instead, the I/O forwarding layer can sort of consolidate that. And now instead of so for each IO forwarding node, you're looking at maybe 1,000 MPI processes talk to one IO forwarding node, and it'll relay system calls back and forth. Now this helps manage scalability, and it lets some relatively old parallel file systems still be productive and high performance components of a modern storage system. But a simple relaying of operations is one step. You can imagine going even further, where you might do some consolidation of requests. You might be able to see that these 10 processes are all writing to the same region. Let me massage that. All the transformations we talked about that were designed and developed in an MPI-IO context could be applied here in the IO forwarding layer. Now, we're still a little ways off to deploying such an optimization, but it's a pretty seductive approach because, again, this is the area where you can get some good scalability payoffs. There are lots of ways you can transform the data. One is transparent to the application, like we talked about. You, as the application writer, don't know that data is being shuffled into under the two-phase optimization or data sieving is happening. But if you were to go into the realm of what we call these not-so-transparent transformations, like this tool developed at Los Alamos called the Parallel Log Structured File System, PLFS, it's a different way of getting around some of the structural and architectural designs of these file systems. You may not, we were talking about writing to a single file, right? And the overhead that incurs, the locking management, the coordination and serialization that can happen. So what if you write to separate files, one file per process? You have a metadata penalty, because now you have to manage order 100,000 million files, but setting that penalty aside, each write to each file happens independently. They're a separate, say, lock domain, maybe is a good term for that. And so PLFS takes advantage of that and sets things up so that while logically the application thinks that it's writing to a single checkpoint, the implementation, the remapped implementation, there's a small index file, and then all the data for that process goes to one file, the data for process one goes to a separate file, and so on and so forth. And PLFS will hide this mostly. Once the application is done, you're left with a directory full of files and you need some other piece to convert it to a non-PLFS format. But because the checkpoints happen relatively frequently and are read relatively rarely, this ends up being an okay penalty, right? You pay this penalty once, and you'll get the benefit possibly many times. So if PLFS is such a good tool, we should just do this everywhere, right? Well, that's not necessarily the lesson you should take. Here's an example from Argonne's machines. We see that small jobs, maybe they're using MPI-IO, maybe they're using a POSIX or a naive IO approach. As we get to be larger and larger jobs, we see the applications either because they've been encouraged to do so or they've been so penalized by the experience of managing many small POSIX files, have all gone unanimously. Any large job here on Intrepid, this is our last machine, is using MPI-IO. And again, we know what they're using because we can hijack their library calls and count how many times they make an MPI-IO call or how many times they make a POSIX call. And we see that for these big jobs, they have, for a variety of reasons, all gone to an MPI-IO approach. And you can do that because, right, the system software will make that manageable for you. Again, we keep coming back to collaborators, but that's really one of the biggest reasons for doing this. These single files are great containers that you can then pick up and take somewhere else. They're using MPI-IO, maybe they're a parallel SDF file or HDF5 file or some other format. But when you imagine you're a collaborator and you're tasked with extracting information from this simulation, do you want to manage a million files, or do you want to manage one file with an index and tools to kind of deal with that? And that obviously, managing the data is a big problem here, and a big benefit. So we've talked about some of the workhorse transformations that happen at leadership machines for a fairly simple storage data model. Linear stream of bytes in the file, dealing with some locking and some other coordination issues from the file system, and how you might overcome those limitations with software. Again, as a climatologist or a molecular dynamicist or whatever your domain is, we're not asking you to embrace these technologies and incorporate them into your own application. Your domain might not even fit well with some of these optimizations, but the idea that the library can kind of package these up and apply them as necessary is sort of the point here. So we think about two things. We think about the model of storage and the application data model. And so these optimizations are where we sort of bridge those two gaps, because the way the application thinks about things and the way that storage thinks about things are often totally different scales in terms of complexity and sophistication. We're going to take we'll talk a little bit about a specific HPC I/O system, the Mira system. So on Mira, just jump here. Now on Mira, we have I'll be bouncing back and forth between these two slides, so sorry, but it's really helpful to sort of show where in the stack, where in the hardware layout, in the hardware topology, these parts of the software stack fit in. From the right, we have GPFS on Mira. It's a couple hundred GPFS servers backed up on a bunch of DDN storage hardware pieces. Then there's an InfiniBand network linking the storage to these I/O forwarding nodes we talked about. The CIOD process on the IBM systems is pretty straightforward, pretty simple. It allows for some number of simultaneous requests, but it's just doing simple relaying of system calls. There's an MPIO implementation on Mira based on the MPitch Romeo package. So I know a lot about what's going on in there and have worked over the last couple of years, past many years, to make sure that those are still working well on Blue Gene machines. You might have a parallel SCDF or a HDF5 or some other I/O library that's going to sort of bundle up all those abstractions into a form that's useful to the application. So again, for scale, 750,000 processes, about talking down to a few thousand I/O forwarders, and the advertised speed of the storage is something like 270 gigabytes a second. And in practice, nobody gets anywhere near that close for a bunch of reasons. But you should be able to get about on the order of 80 to 100 gigabytes a second, I guess, for well-formed writes. But you need the whole machine to get that point. If these I/O forwarding nodes also serve as a way of sort of you only get the best performance, the highest performance at large fractions of the machine. You're not going to get 270 gigabytes when you have one compute node driving one I/O forwarder. You need to have all these links working together. And again, that necessitates MPI frameworks and I/O libraries, because managing all that parallelism is quite a task. So, as you're thinking about how these optimizations fit into your personal domain, there are, you as a client of these machines don't get a lot of say into what file system is running. There may be a crazy fast research parallel file system out there, but the administrators of these machines are going to deploy what hit the procurement said file system. They got a file system, and that's never going to get touched. So we sort of have to deal with the hand we have, and we do that with all these different libraries and software pieces. And as you are working to understand these problems, these libraries help to bridge the technological gap, but also sort of a social gap, right? If you come to me saying, I'm trying to model these particles, I don't know what's going on, I may not be able to be as much help as if you say I'm using HDF5 and I used these, I turn on these flags and here's my data set. Why is this slow? And we can look at layouts and optimizations and ways of tackling it in a context that we both understand. So with that, I'm going to turn over the floor to Rob, and he'll start talking about our first code example. Oh, great question.
So I'm just curious, related to what you said. So basically, if you have an application and you are running on Mira, but you might also run it on several other platforms, they might have different characteristics.
Yes, exactly. Okay, so the question was, you do all this, you're running on Mira, and you learn how Mira works, and now you go to another machine, and the characteristics are all different. And what the questioner is touching on is this idea of performance portability.
And how many modifications are required to kind of keep consistency among all this?
So, right, what is the scope of the changes needed to get best performance out of, say, Titan and Mira with the same code base? Well, the answer I want to tell you is that it should all be kind of painless. You do the HDF5 I/O, and the vendors have made the MPI on Mira good for Mira, and the vendors have made the MPI I/O for Cray good for Cray, and everything works really well, and you never see a difference. But of course, over the last 5-10 years, we see that's not the case at all. I do think, though, you can probably today it's a lot. Sorry, the gap in performance the performance portability story is a lot better today than it was 5 years ago. The MPIO library on Cray is a lot better suited for the Lustre file system. Some of the optimizations we talked about have been incorporated. I think, also the staffs at both sites understand the interaction of all these layers a lot better than they did when we first started these leadership scale machines 5-10 years ago. So I think the story is more hopeful. Maybe I should ask you a question. Are you speaking from your own suffering? Have you had a problem going from one machine to the other, or are you more worried about?
I always suffer with IO.
You always suffer. That's unfortunately common. Yeah. What I would say is that the use of these I/O libraries is a good first step. It then reduces the amount of tuning that. Well, it adds more tuning possibilities, but we know for Mira do these three things, for Cray do these three things, and that generally makes it a little bit easier to isolate the different platform-specific tuning that has to happen. As time goes on, the story's going to get better, but we're still working on making it super painless, I guess. Sorry you're having such problems. Any other questions? Yes.
Yeah. So the earlier example you showed, you were saying instead of having each node, each process write contiguous, you sort of rearrange everything.
Yes.
I mean that pattern there is like an MPI all-to-all in a sense. Is there like a trade-off point where the network communications of doing that, a certain size, starts to cost more than the I/O saving?
So for the answer for a machine like Mira is the trade-off is actually pretty far down the road. The all-to-all, and that's exactly how it's implemented on Mira, is with an all-to-all communication, has been optimized to a pretty great degree, and you can ship a lot of data over these networks. You can ship, I think the balance is something like 100 to 1 performance, 200 some gigabytes to the storage system, no, sorry, I'm getting it wrong. Well, anyway, I'm not sorry. I'll have to get back to you the exact numbers. But the network is so much faster than the storage that you can really do a lot of movement before you pay the cost. But it is important to understand that trade-off, and there are ways to turn off this optimization if you know that you're going to be writing in a way that's already good enough. And it's often easier to turn off the optimization if you see it's not doing any good than it is to try to reorder your code to take advantage of collective I/O after the fact.
The other thing that happens in this case, the really bad case for this right now is that if you have a very, very large number of very small regions on each process, the way currently these algorithms under the covers sort that information and generate the schedule for the right-hand side doesn't use memory particularly efficiently. And so that it's not, it can sometimes not be the communication so much as this, this sort of schedule building process that ends up being the thing that makes it not worth your time. And knowing that can sometimes mean that you can do some local restructuring of your data and then still get the collective I/O. But that's a place where Rob has actually been doing some work recently to try to cut down on the internal memory utilization of the library in response to seeing some particularly bad collective I/O behavior. Yeah, it's definitely a legitimate question. It used to be the systems were much better balanced, and so it was a lot harder to know whether this was going to be a win or not. And now the I/O systems are so slow relative to the networks that it's almost always a win.